morning, everyone. My name is Alessio Figuretti from Tesla Vehicle Attribute team. And it's a real pleasure for me to be here today and be with you presenting today. After all this presentation about vehicle dynamics, let's change a bit the frequency range and let's talk about noise and vibration. And today we'll talk to you about a global NVH challenge that most of the company face. How road surface variability across regions affect masking noise, and also how we could account for it in a consistent and scalable way using NVH simulator. I think Tesla, as a company, doesn't need an introduction, but let me spend some word about the European Vehicle Attribute team. The European Vehicle Attribute team is located between Ideal Proving Ground in Spain and the Tesla Gigafactory in Berlin, in Germany. The fact that we are located in two different countries already give us frequent exposure to regional differences in road surface and subjective perception. And this is also one of the points that motivated the work that I will present you today. The global NVH objective of our team is quite straightforward: deliver optimal and consistent NVH performance across all vehicle programs. The challenge is that a single vehicle program is validated globally and is produced in multiple sites and tested in different tracks. So each of them has different characteristics. Let's consider, for example, Model Y that is produced in 4 different sites and validated on 3 different proving grounds. So the same car can sound very different, depends on where it has been tested. The fact that most of us that are involved in testing are really aware is that road surface variation is one of the biggest variability issue during the testing. In fact, the texture of the road can vary region by region due to different construction standards. Several studies investigated the average roughness of the roads across the world and highlight that, for example, in general, Europe surface are smoother compared to North America or Asian surface. On the center, we can see a comparison with 2 surfaces defined as smooth, one from Europe, the green one, and one from US, the blue one. And this is the spectrum of the drivers here. You can clearly see that while the low-frequency region is more or less similar, the middle frequency region is quite different. And why this is so important? Because the texture difference in the road will change the road noise that act in the band, particularly in the band of 50 and 2000 Hz, and especially for EV vehicles, is the primary source of masking noise. And so having different masking noise can hide some issue, for example, powertrain noise or accessory noise on some surface, while being more evident in other. This will result in having local dependent subjective and objective data and a real risk to have an inconsistent sign-off across different regions. So how we could take this into account? In theory, we could think, okay, let's resurface all the tracks where we usually test to have the same road surface characteristic. But in practice, this is unrealistic because usually test tracks are not owned, and the cost and timing to do so is really extensive. Another possibility would be to test everything on chassis dynos that for sure provide more control and efficiency. But then, as we know, this does not fully capture real driving condition. So the key question is, could we use the NVH simulator to evaluate vehicles in a consistent way and in a smart way without the need to physically test them in all of them? To verify this approach, we started first acquiring data on different surface around the globe, and to build a simulator model. So we collect all the data in order to have the possibility to discretize the vehicle in its main noise contributors. So dividing between road noise, wind noise, and specifically subdividing road noise in structure-borne for the front and rear suspension, and the airborne contribution coming from the tires. Once we have all these roads identified into the simulator models, we perform global subjective driving assessment on the 3 simulators that we have on the 3 different regions to perform virtual subjective evaluation independent on the location, and also to assess if, with all the NVH team, if the different texture on the road were perceived in the correct way. After this step, the second step was to calculate a masking noise scaling factor. And so we started measuring a reference surface, and starting from that, we consider a frequency-dependent transfer function between the reference road and a target surface. Once we have calculated this transfer function, we apply directly on each road noise contribution inside the NVH simulator to retrieve, let's say, the scaled road noise. In this way, it was possible to create a standardized library of test track surface, also enable repeatable evaluation, but still having everything grounded starting from measured data. The final step, that is also the most important, was the validation. We validate this methodology using multiple vehicles and multiple scenarios. The goal was not only to achieve correlation, but also to build confidence on this methodology and to identify if was clearly capture the difference between the surface. So we tested different scenarios. The first one was a sort of a sanity check. So we we use the methodology to predict the road noise change on surface acquired on the same track. The second one was to predict how a vehicle will behave on a surface that was recently resurfaced. And the third one is a cross comparison between 2 different regions. Let's start for the first example. So in this case, we started from a reference smooth surface, and we wanted to calculate how this vehicle will behave on a rough surface. So using the transfer function for this model, we calculate the prediction, and as you can see, the correlation between the prediction and the measured data are really close. We have a delta below 2%. So this confirms that the frequency-dependent scaling capture well how the road is changing. The second example is about the resurfaced track. In this case, a vehicle A was measured on a track that was not existing anymore. So we used the data from this vehicle acquired on the smooth surface to calculate how he will behave on the new asphalt. And even if the surface characteristic is really different, we can see that the response remains within a range of 10%. So it's quite good results. And this is really important because the resurface events are common in a test track, and often invalidate all the historical reference. So having the possibility to predict how the car will sound on a new surface is really important for us. Last example is a comparison of vehicle acquired in US. So in this case, we started with the vehicle measured in US, and we wanted to understand how they will behave on Europe. So as you can see, even if both asphalt were defined as smooth, the response is quite different. But using this methodology, we were able to let's say, to bring the vehicle measured in US to a similar level to the EU smooth asphalt, with a difference, also in this case, lower than 10%. But now let's see a practical example of everything that we have discussed so far. So in this case, we are talking about a powertrain noise evaluation. So a vehicle was assessed in North America on a smooth surface, and the question is how this vehicle how the powertrain of this vehicle will sound on an European surface. So using the NVH simulator, we build a model from the data measured in US, and using the transfer function, we scale the masking noise considering the European asphalt. And doing so, we can see that the powertrain component is 20% more prominent compared to what is perceived the vehicle in US. So this is really important, because in this case, nothing has changed in the vehicle, but just the road surface itself. And something that probably in US would have been considered as okay, could be an issue on a smoother surface. To conclude, road surface variation is a fundamental challenge for NVH validation, but combining the NVH simulators with masking noise scaling provide us a scalable and data-driven solution. It improves consistency and reduces the dependency on physical testing across region, and support faster and more reliable global sign-off. In the end, we can now predict how a vehicle will sound and feel on any major test track surface that we are using without the need to being there. Thank you for your attention. If you have any question, feel free to reach me after the presentation.